How's it going? Welcome to my final lab report, Physics 2212, Lab 6, Faraday's Law. The purpose of this lab is to explore the induction of currents due to magnetic fields by dropping a physical bar magnet through an aluminum tube, and then comparing those findings with a computational model. The materials in this lab include a bar magnet, aluminum tube, and the computational model will be delivered using Glowscript. The system includes the bar magnet and aluminum tube, while the surroundings contain everything else. The fundamental principles of this lab include Faraday's law, which states that the induced EMF of a system is equal to the negative change in flux over time multiplied by the number of turns the system has. This experiment also implements the Biot-Savart law, which is used to calculate the magnetic field of the magnetic dipole of a falling magnet, while the delta V equation can be used to calculate the induced magnetic field produced by the tube of aluminum as a result of the dipole. Lastly, Newton's force laws apply in this experiment, particularly the second law, which states that the net force is equal to the change in momentum of the system over time, and the third law, which states that for every action force, there exists an equal and opposite reaction force. This is a video of the physical experiment. The procedure in this experiment was very simple. Drop a bar magnet vertically through the tube and record the time it takes to come out the other side. It was very important, however, that the north end of the magnet was facing towards the tube to make this calculation more simple. However, if it had been oriented the other way, the result would still be the same, as the induced current would act oppositely to produce the same effect. The data collected from the experiment is shown here, along with the properties of both the tube and the magnet. Ultimately, across 5 trials, the average time for the magnet to fall through the tube was approximately 1.3 seconds. This is the first part of the code used to generate the computational model. First of all, I import the experimental properties of both the tube and the magnet so that the simulation is as accurate as possible. Then, I define a function which calculates the field due to a dipole, which is identical to the formula presented in the Biot-Savart law earlier. Lastly, I create a function that calculates the change in flux over time, which will be used to calculate the induced current. Before moving forward, it is important to note that gravity is obviously a force acting on the magnet as it falls, so we must account for that. Moving forward, the change in flux over time calculated previously is applied to calculate the current. This is a direct application of Faraday's law, as the EMF is equal to the negative change in flux over time. Since EMF is also equal to current or resistance, the change in flux is divided by the ring's resistance to get the current. Next, the force on the ring is calculated using the current and the formula for calculating the magnetic force on the ring. The angle theta is used to determine the direction of the field with respect to the vertical. Next, Newton's third law of reciprocity is applied, as any force applied on the ring by the magnet will be reciprocated to the magnet itself by the ring in the opposite direction. Since the x and z components of magnetic force cancel out, the only force applied is in the y-hat direction. Lastly, Newton's second law is used to find the net force and update velocity and position accordingly. This is the output of the computational model. At first, the force of gravity is stronger than the magnetic force on the magnet before it falls into the tube. As it enters the tube, force of gravity is approximately equal to the opposing magnetic force on the magnet, which causes it to travel through the tube with constant velocity, as the net force is 0. Lastly, as the magnet exits the tube, the magnetic force stops acting on the magnet, so gravity accelerates it again. Critically, the computational time that it took for the magnet to travel through the tube was 0.876 seconds. So what are some interpretations from the computational model? In the previous visual, a red and blue current was flowing as the magnet fell. When viewed from above, the red current flowed counterclockwise and the blue current flows clockwise. And this it was derived using Lenz's law, which states that the current flows in the direction of negative change in flux. So what if we flip the magnet? It wouldn't change the time it takes for the magnet to fall through, but the direction of current would flip to compensate for the reversal of the magnetic dipole moment. The simulation time differs from the real time and is slightly faster, likely because of real-world factors such as human error and air resistance. Lastly, the plot shape, as explained previously, shows that the force of gravity trumps the magnetic force outside of the tube, but the two forces are equal inside the tube. To reiterate, the computational models assume no air resistance and that the only forces acting on the system were gravity and the magnetic force of the objects in the system. In reality, there are several other factors in the experiment, including drag, human error, friction between the tube and the magnet, and, to a lesser extent, the magnetic field of the Earth. What if the resistivity of the conductor was as close to zero as possible? Because EMF equals I over R according to Ohm's law, decreasing the resistivity decreases the resistance, which would cause a stronger induced current and opposing magnetic field, slowing down the magnet further. What if holes were cut into the tube? This would effectively cause there to be less rings in the tube, which weakens the opposing magnetic field and causes the magnet to fall faster. Thank you very much.